Hi, in this tutorial I'll take you through a little ISETBio tutorial on color matching. So first let me share my screen. I think what I'll do is share the whole desktop, get rid of that. And what I have here is my Git client, and if we look at the ISETBio distribution, there's a folder called tutorials, and in there's another folder called T_color for color tutorials. In there is a tutorial called T_color matching. And I'm going to bring that over here to my MATLAB editor. And let's make that nice and big so we can see it. What we'll do is go through this. So typically at the beginning of an ISETBio script, we might run the standard initialization routine, i.e. init, which just sets up some variables for us and some other things. Don't need to worry about that too much. And now what we want to do is think about how to get some spectra to play with and to work with. And for this tutorial, we'll sort of be talking about color matching in the context of displays. So what I'm going to do is run this little bit where I use ISETBio to get one of the pre-populated display files that gives properties of display. This one is for an old Dell CRT. And I can get, once I have that, I can, on the display object D, I can call display get, which, and with various keywords, this one will get me the wavelength support, with which spectral files are provided in that display, so I'll do that. I might be interested in knowing the wavelength spacing, which I can get just by taking the difference between the first two wavelengths. That's probably, let's see what that is. That's 4 nanometers. And then the other thing I'm going to want is the spectra of the primaries of the display, which here are called phosphors, because this is an old CRT, which use phosphor-based technology. And so I can get from the display the spectral power distribution, SPD, of the primaries. Great, so I've got those. They dumped out here as numbers in my command window because I forgot the semicolon. But let's just take a look at these. We can get a plot by bringing up a new ISETBio graph window. And here we see the spectra of the red, green, and blue primaries of this display. These are typical CRT kind of looking phosphors with the 2 spikes in the red primary. So I have 3 different primaries there that I can work with in this tutorial. I don't think we'll need this figure again, so I'm going to close it. And now one thing we might want to get is the color matching tristimulus coordinates of each of these phosphors. And so to do that, we're going to need the CIE XYZ color matching functions. And we have those as data within ISETBio. So we can just go grab them with this simple command here, i.e. read spectra. We want XYZ, and we are going to get them at the wavelength sampling that matches that we set up and have in our display. So now I've got those XYZ values. We can go ahead and plot those. And these are the familiar CIE X, Y, and Z bar color matching functions plotted here as a function of the wavelength support. And again, I don't think we really need to keep this graph around, so I'll close it and we can go forward. Now we've got the color matching functions, and they're in the columns of a matrix, and we've got the phosphor spectral distributions, and they're in the columns of another matrix. So if we take the transpose of the color matching functions times the phosphors, that's the dot product. We need to multiply by the wavelength spacing here to keep the total power correct, since phosphor power is going to be in something like watts per nanometer and what other geometric factors there are. And then this 683 here puts the Y value, makes that luminance in candelas per meter squared. So that's a unit constant that's standard when we are the phosphors in, and when they are in radians of watts per nanometer per meter squared per steradian. So I'll execute that. And that gives me a little 3x3 matrix where each column is the X, Y, and Z values of the red, green, and blue phosphor spectra of this monitor that we're playing around with. This just tells us what the maximum luminance is of the display, because it's the, of each channel. So that's the 21, 67, and 11.9. Those are in candelas per meter squared. And if we sum those up, as I do here, then we could get the total maximum luminance of the monitor in candelas per meter squared if all 3 phosphors were turned on. to their maximum amount. ISETBio actually provides a shortcut for this calculation, which is IE XYZ from energy, where we just pass it the phosphors transposed and the wavelength spacing, and we can get that. And you'll see that I get the same matrix here as I had up here. So now we know the XYZ values, the color matching coordinates of each of the 3 monitor phosphors, which we have in this matrix, which I'll keep using, and this just shows another way that I could have gotten it. Great. So now we want to sort of show how it is that we would find a metamer, a perceptual match to an arbitrary spectrum. And we have one here that sends back a measurement, and I believe this is one of some spectrum measured on Mars by a rover that was landed there. And we have this again just in the ISETBio database. So I'll get this Mars spectral power distribution, and I'm again asking for it on the same wavelength sampling that I have everything else that I'm working with here. And we can just plot that to see what it looks like. Here it is. It's got this particular shape, and this thing drops off to 0 because we've asked for it on a longer wavelength support than the original data, and it just 0 extended the spectrum there when I loaded it. Again, we don't really need to look at this anymore, so I'll just put it away to keep us from getting too cluttered. And now we want to know the XYZ values, the color tristimulus coordinates of that spectrum. And again, I already showed you this function, I XYZ from energy. So we'll just do that here. And now in the variable Mars XYZ, I've got, I guess in this case in the rows, I've got the XYZ values of that Mars spectrum. Now, what the principle of color matching is that if 2 lights have the same color matching coordinates, the same tristimulus coordinates, they're going to look the same. So we want to find what combination of our monitor phosphors would we have to have, what mixture, to produce the same XYZ values as we got from this Mars spectrum. And the first thing to observe is that we can basically compute those total spectrum of any mixture by taking the phosphor spectral power distributions, which are in the columns of this matrix, and multiplying them by a column vector, which gives the relative contribution between 0 and 1 of each of the phosphors to a mixture. So if I just wanted to pull out the red phosphor alone, I'd use 1, 0, 0. And these are what we might call the linear RGB values, because we're assuming that there's no nonlinearity between these relative strengths and the actual spectrum for this example so far. And we could just evaluate that and plot it. And there it is. That's the red spectrum that we saw before as one of the 3 phosphor channels in the original graph. Again, just get rid of that, keep things from getting cluttered. If we wanted to see the mixture of the blue and green, we take the phosphors times 1, 0, 1. Again, transposing to keep this in a column vector so the matrix multiply works correctly. And we can do that. And I don't want to interact with my charts, which MATLAB seems to want me to do. But there we go. The green plus the blue plus the red. I may have said that wrong earlier on. Okay, so now we've seen how to produce various spectra as weighted combinations of the phosphors using little matrix multiply. What we want to do now is find the relationship between the RGB values we need and the monitor XYZ outputs so that we can compute metamers, as I'll show you below. So first thing we'll do is actually recompute our matrix that we called max XYZ before, and I'll do that right here. This little transpose puts the XYZ values of each monitor channel in the columns, and so we can just see that what we have in mon to XYZ here is the same as what we computed above as max XYZ. Those 2 matrices are the same. And if we multiply this matrix by RGB values here, what we get, because of the linearity of color matching, is the XYZ values of the particular combination of the monitor phosphors. Another way to get that same matrix is just to use this shortcut with the display object. So there it is, again, computed exactly the same, but with this shortcut. Now, what we want to do is find the RGB values, the weighted combination of the phosphor spectra that produces the same XYZ values as the Mars spectrum. So just to recall, here those are this particular set of numbers. They're rather large and larger than these, so we're going to get relative values that exceed 1. And we just use this little linear regression command here to find that. But I'll just show you here. We get Mars RGB, and that is the RGB values that you multiply by this matrix to get those XYZ values. So let's just check that. Here we have check XYZ is that, and this should be the same as the Mars XYZ values we were after. And here's the Mars XYZ values, and these numbers here are the same as those numbers there. Another way to do this, just in case you're more familiar with, would be to take the inverse of the MON to XYZ matrix and multiply it into the Mars XYZ value. Oops, if I can type it right. What have I done here? In MON to XYZ times Mars XYZ. Somebody isn't happy. I need to make it a column vector, and there we go. So those numbers there ought to be the same as these numbers here, which they are. So this little inverse matrix is the same calculation as this regression version. We've checked that it gives us what we want. So now we can compute the metamer to the Mars spectrum as a weighted combination of the phosphors by just doing this little matrix multiply, weighting the phosphors by the RGB values. And that gives us a spectrum, and we can just check that the XYZ values of the metamer are the same as those of the Mars spectrum, which is what we want to be true in the end. And so there those are. And if we look at the Mars XYZ values, and these numbers look familiar, but let's just make sure that they're what we expect. Yep, so that all works out. And now we can display both our metamer, which I really should have here as, I might as well type this in as metamer SPD rather than computing it again. And we can display that and one subpanel. So this spectrum here, which is a mixture of the 3 monitor phosphors, produces the same tristimulus values as this Mars spectrum here. And since the XYZ values are the same, these are metamers.